So howdy all. I'm Stanislav Láznička. I'm a principal software engineer at Microsoft. I am a Kubernetes contributor, and since recently I am also a member of the Kubernetes Security Response Committee. Today we will be talking about cache and file system access, or really it's about caching in general. If my stuff's broken, oh no. There we go. All right, off to a good start. So let's get right into it. Caching, I guess, I don't really need to introduce much. Everybody knows what this is. Yeah, if you've got something that is perfect, like you're accessing something, or you have something which kind of computes for a long time. There's a good chance that you can store the results of the compute or of an I/O operation inside of a cache, which is some kind of a constant complexity access level thingy. This is easy. Even old babushka knows how caching works. So this is all great. The thing is, in real life, stuff isn't always that simple, right? And it all pretty much comes down to the fact that we do not have infinite memory, right? And so once you realize that, all of these things, that's what I would mostly just call engineering, right? You need to understand your use case. You need to make an educated, not a guess. You pretty much need to pick from the choices that you either know, or you Google, or you chat with an AI about, and then you can use that in your system somewhat effectively, hopefully. And so when you're making this choice of a cache that you may want to use, you may have several choices. You can pick the cache by when and by whom a record is made into the cache, right? There's this line about data store access. Or you can, but usually you will also pick the strategy of how size limitation is being handled in the cache, right? And there's a bunch of things. Pretty much like this, this strategy tells you which records you should drop from the cache when you want to make a new write when the cache is full, right? I'm not going to go into details in all these things. I will share the slides later. There are some links in here which basically describe these things in detail. I thought that I would just bore you to death if I went line by line. So instead I will show you what I did, which is either worse or better. We'll see. Anyway, one of the things that I'm seeing the most, or the caches that I've pretty much always worked with, were LRU caches, the least recently used caches. And so I put some examples in here. A really good LRU cache is a Golang LRU cache by HashiCorp. If you can have a look at this. I say here that the MPL license may not fit everyone. There's a link to a Kubernetes PR, which pretty much introduces this other thing. But MPL is actually just fine open source license, so don't worry about that. And here's a second example you may want to look at if you would ever want to implement an LRU cache yourself. The Kubernetes example is a little bit more dated. It's like a fork from Golang from 7 years ago, but it actually works just fine. And we'll probably have a look at, well, not probably, we'll have a look at it a little bit later. All right. So let's get into the fun stuff, the thing that I actually did, right? And so the problem was this. I was writing a feature which was guarding access to private images that are being pulled on Node. I was basically implementing an authorization layer, right? And in the alpha phase of the feature, what we did was we were just storing the authorization records as JSON files on disk. You may think that this is kind of a weird choice, right? But this is what we did. Like there are reasons for it, mostly like observability of the system in the alpha phase, right? And we knew that we eventually want to do something which performs a little better. So we knew that we want to introduce a cache in here. Another thing that we will have to count on is concurrency, right? The records will be the records on in the system will be accessed concurrently, meaning there will be many readers or maybe even writers trying to access the records. When this is because when a pod is being created, it's not just a pod. Like you can have multiple pods being created at the same time on a node. And that means that all of these will be accessing the images that are running inside of the pod. I'm not sure how much you know about Kubernetes. I'm only going to be touching it a little bit later. So if you don't understand some terms, don't worry about it. Just understand concurrency. Now, the system that we are working with, we know about some constraints that it has. The system that we're working on is basically the kubelet is supposed to start other processes on the same system that the kubelet is running on, right? So that means that it is sharing some system, and that means that like many of the resources all of the resources honestly are being shared, like the resources of the system. And luckily, we actually know that the recommendation is that there will be about like 110 pods running at a time for big clusters in Kube, and so like this is a constraint that we know that we can work with, and like this will influence how we will situate the size of the cache. But that's not the only constraint, right? Kubernetes is actually being deployed like in all kinds of different and weird systems. So like while you can have like huge clusters that are running in, say, like Google Cloud Engine or something like that, like huge clusters, or even in Azure. There are people who are running Kubernetes clusters like in McDonald's kiosks, right? I heard about those use cases. It's odd, but like apparently that's the best thing that we can do these days. Like have a small Kubernetes running there, and this kind of influences the fact that this influences the way that we need to implement the cache. We need to take all these things in mind. We need to keep these things in mind, and we need to be able to scale the cache, depending on some variance of the system. If you are interested in like the actual thing that like the whole design of this private images garden, this is all in Kubernetes KEP 2535. There's going to be a link in the slides. So, all right. We know that we want a cache, and I said that LRU caches are really most common, at least in my area. So I'm going to show you a cache. Can you see this well? This is fine, yeah? So this is actually the Kubernetes internal cache that I showed you in a link earlier, right? And this is an LRU cache. And it has a couple attributes, right? Like max entries, that's quite obvious. Like we want to be able to know, we want to be able to set the size of the cache so that it doesn't grow infinitely. Evicted function is a function that I will get to in a little bit. You have a list here instead of just a map, which may be a little bit confusing. But since this cache is tracking like the least recently used items, it needs to track usage of the items, right? And so whenever you are actually accessing an item in the cache, either via get or set, you take the item that you accessed and you put it on top of the list, right? And this is actually really neat, because you probably know that like if you wanted to get an item from middle of the list and put it on top, like you can do this in constant time, right? You just splice it out and then you put it on top. So like this is cool. This is fast. We like it. And obviously you have eventually a cache of all the items or like map of all the items, so that you can access it easily, right? It's just a map of the items of the lists. Quite easy. Now, since we are interested in what happens on write when the cache is full, let's have a look at that. So, you are doing a set on full cache. So what happens is you take the last item from the list. Remember that the most used items are on the top, and the least recently used items are at the back of the cache. So you take the last element and you just drop it. But like this can happen maybe sometimes a little bit unexpectedly for the user of the cache, and so we let them know by using the onEvicted cache. This is basically like, I evicted this item. I'm going to call this to let you know, right? So that like it's kind of easier to track. Woo. All right. So now that we know what an LRU cache looks like, and like you can see that this cache is actually not thread safe. Like this is the internals, the actual cache that you would get to use would be locked from the outside, right? So like the cache that Kubernetes provides you will be locked, would be thread safe. This is just an internal implementation. One thing that I will say is, and that one thing that is interesting if you would want to implement your cache is, what do you think happens during get? Is get like a just read operation? Could you use read-write locks? You actually couldn't, right? You need to be locking properly, because a get operation is also a write operation in the LRU cache, because you are modifying this list. So you can only use normal locks, not read-write locks. That's one interesting gotcha. All right, but enough of that. Let's go to the real life again. So in real life, you've got your beautiful LRU cache, which is thread safe, because you use the thread safe variant, obviously. But you also need to feed the cache data from somewhere, right? And you could do it, on cache misses, for example, or you could pre-feed the cache. But the thing is, this way, if you've got a cache miss and you need to fall back to the data store, like this fallback is actually quite expensive, right? You're trying to avoid it, and so like if you were on each miss, if you were just accessing the data store, like that would be just direct file system access with extra steps, right? Like you just put a bunch of steps in front of it with a bunch of locks. And so the way we dealt with this, and this is kind of specific to our use case, is we are actually using a warm cache, meaning when the cache is being initialized, we put all the records in it, because we need to list all the records on the disk anyway. So like once we have them, we just push them into the cache, and that's really useful, because we can then introduce what we call cache authority. Now this is really simple. The cache authority just means that like if the size of the records in your data store is smaller than the size of the cache, then the cache is authoritative, which means that every miss of the cache is authoritative, which means on a miss you don't need to go to the data store, right? And so this way you can see that the size of the cache actually becomes quite important, right? Because like this pretty much determines how your system performs, right? We do not want to crash the system once we have way too many records, because we still need to go on, and but the user should know, and there's a metric for that the cache was being full, and they might fine-tune some of these parameters. You can see from all this that you should always strive for the authoritative mode, which we are able to do. Like during the normal life cycle of the cache, we would only ever go from authoritative to false. But luckily on kubelet, and since we're dealing with records that are related to images, kubelet does garbage collection of images that are being unused, right? And so on each of this garbage collection, we do the whole list of the file system records again, and we update the cache. And this way we can go back from non-authoritative to authoritative when the size of the data store is smaller. All right, so there's one thing, right? Like actually being performant, but another thing is how to deal with concurrent access to the cache, right? So we know that the cache itself is thread safe, but for each query that we got, we can also fall back to the data store, right? Or not necessarily query, but if we're doing writes, we want the writes to propagate to the data store, right? And so we need to guard this access so that like two different writers aren't trying to write inside of the data store. So you could just do global logs, but that would be very good solution, right? With it, because like then one expensive action would just block all of your cache, right? And so like you ideally want to use some kind of a data structure which lets you use named logs, right? And so the signature of whatever you would use would probably look something like this. Now, what could that data struct be? You may think that a sync map with mutexes would be a good idea, but you would probably also forget that we are in a system that has limited memory that it can use, right? And so we cannot just grow this map in the like infinitely. So yeah, we are trying to be the good guys. And so, like I said, memory constraints always apply. And like, if you wanted to remove a log from the map, like think about it, like when is it actually safe to remove a log from a structure like this? That's not that easy to do. And so you will eventually end up thinking, well, maybe I could just, since I'm dealing with like restricted memory, like not restricted, but like small chunks of memory that I will own. Like maybe I could just pre-allocate a bunch of logs and just use them somehow. And that's what we did actually. So there's this thing called striped log set. And I don't know if you know what striped sets are, but like I didn't read the exact definition of it, but the way I like to think about it is you have a set, right? And you are trying to access it with like all kinds of values, and you always need to map these values inside of the set, right? And so like if you imagine like the indexes being numbers, when when you put like the groups of numbers that like map to the same thing, next to each other, you'd kind of get these stripes, right? So that's how I think about it. Now, how this actually works is you've got your logs, which is just like mutexes, and you get a size of the striped log set, just helpful here. When you are locking the set, you lock a specific log which you access by some kind of a mapping function on your key, right? And since, like I said earlier, we will be doing some kind of garbage collection, we actually also need to implement like global lock of the case so that we can access all the records from the garbage collector, right? And now the most fun part, I guess, is like the mapping, which you can do, and this is actually very commonly done by using the FNV hash, because hash is able to take any input and just return a number. The FNV hash is considered to be quite fast, and you want that, right? So like you just hash the key that you're getting when you lock in, and you just mod that number with the size of the slice, and this way you get those stripes that I was talking about earlier, right? So yeah, so this is neat, I think. So let's now summarize what we've got. When we want to write inside of the cache, this is actually quite simple, right? Like you log the cache by the record name. We know how that's logged now. You call a defer, so that everything the log gets unlocked eventually. You just write the record, and then you write the record into the cache as well when the first write is successful. So simple, like there's no magic here. Now the reads get a little bit more interesting, right? So ideally, you want to do the cheap lookup first, right? You just do a read, and you try your cache, and you see what happens, right? Now this slide describes the worst case scenario, in which this is a miss. When a miss happens, you need to log the cache by the record name so that nobody writes the records in the meantime. And interestingly, you need to do the get again, the cheap get, because somebody could have written inside of the cache somewhere in between 1 and 2, right? This is concurrency. This is cool, I think. So yeah, now when you get a miss here again, like your last straw that you're grabbing is like, maybe the cache is authoritative, right? Maybe this is fine, and I can just return the miss, like we don't have this. But if the cache isn't, and like this is an atomic bool, right? So that we're all safe. If the cache is not authoritative, well, we have to go to the data store, do the expensive operation, and if we finally got a hit, we just set the record in the cache, which, funnily, can cause is authoritative to be false, because we could write a new record into cache, right? All right. Yes?
Do you like to take questions now? Or
if you don't mind, I would do it in the end, if that's okay. Yeah? Okay. All right, thank you. But I'm really looking forward to it. All right, so now we have our cache. Life is great, right? Everything is beautiful, but we don't know whether it works yet. Like, we can probably test, like, technically that it works, right? Like it returns stuff when we ask it for it. It's probably the correct things, right? But since we were trying to do something that increases the performance of the system, we actually need to check that the performance got improved, right? So that we didn't just add a bunch of steps on top of the previous sections, right? So it's not like direct access with extra steps, so because we can, right? And so like you want to do some benchmarking for your cache, and like I don't do a lot of benchmarking. I don't know about you. I asked some speakers yesterday. They also mentioned that like this is not that very common, and so this was all new for me. Maybe it will be new for you. Maybe you will be bored for the next 7 minutes or so. But yeah, let's do it anyway. So when you're benchmarking your stuff, right, you need to take, you need to consider what your cache would look like in different cases, right? You need to consider like, so what happens if my cache is small? What happens if my cache is large? What happens if there's like 5 times more records than what I'm able to store in the cache? What happens when there's only like two times more records on the data store than I'm storing in the cache? Like, at which point do I start being ineffective, right? So like, these are things that you would test. Like we know that the cache has some kind of a authoritative mechanism, so we're going to test that with the number of records, obviously. And you may also consider like what happens during a cache miss, what happens during a cache hit, right? So these are also different scenarios. Like you want to make sure that everything works well and that it performs well also, right? And another interesting thing is we have logs in here, and we introduced some kind of a structure of logs, and we do not know what's the throughput of it, right? And so like, how do we test that? Now, I do not know if this is the right solution, but this is the solution that I've got, right? So I didn't find any good way in Golang to say, you see, I've got a log set of size 2, and I would like to run n Go routines on top of it. What Golang does let you do though is to set parallelism for your benchmark, which means that like the benchmark in suite will run p times p being the argument of set parallelism, p times gomax pros test coroutines. So this for me meant, well, all right, I'm just going to set the stripe block set size to runtime num CPU because I know that I will be running this benchmark myself, and I will always use all my process for it. And I'm just gonna set p to the times of the size of the cache this way, right? And I know that at like p equals 1, we are like closest to true parallelism, right? Because we are running on each of the cores, and whatever else is just that is actually becoming concurrent access to it, right? This may not be that important, but it's I like to keep it in mind, right? Like something happens in there which is using like more cores than what I really have. So okay, we now know a little bit about benchmarking and how we want to do it. Let's just briefly look at the basic structure for the benchmarks, just in case you've never done it before. So when you're testing everything in like serial, like not in parallel, in some version of Golang, they introduced a b.loop, which just is a simplification of what you had to do before. So you no longer need to reset your timer, so you don't need to clear any counters. This does it all for you. And so typical benchmark looks like you are initializing a bunch of structures, preparing the test data. Then you start the benchmark, and then eventually you clean up whatever you want, and everything goes down, right? So that's not in parallel testing. Testing in parallel is a little bit more difficult. No, not really difficult. You pretty much do the same things, only you need to set the parallelism as we described earlier. You then need to reset the timer because I believe that this doesn't do it for you anymore. And then you do b.run parallel, which is gonna start the number of Go routines described here, and then eventually you stop the timer and you do your cleanup. Now, before we have a look at what all of this spits out at you, let's just look at what you would do, how you would typically run your benchmarks, or like these are the best practices, right? You ideally want to be running in an isolated, stable machine with little to no activity, because like you don't want your browser to be taking the cores that you would otherwise be using for a benchmark at weird times, right? This will just pollute your results. You do want to test minimal code units. This might be obvious to you, but I did a bad mistake here where I was trying to test the cache at a bit of a higher level, and there were just so many other things happening that the results were completely unusable. So always test like the minimal code units that you would probably otherwise test in unit tests. Now you also want to run each benchmark multiple times. Golang has an option for you, which is this one, this count 10. And this lets you see, what are the deviations of the deviations of the usual run, because like otherwise you just run it once and you don't know if like this is any kind of significant result or whether just something weird happened through the run. When the deviations are too high, you know that you're doing something wrong and that you should probably fix your benchmark, right? And so when you want to when you want to benchmark your code, you just run a command like this, something like that, whatever fits your needs, right? Now, this will spit out a lot of text at you that you can probably look through manually, but like you wouldn't probably learn too much. There's a good tool that lets you analyze the results a little bit better. This is benchstat, and it lets you do a bunch of funny things, like it will display results and columns for you based on a filter that you can set, right? So like in this case, we are filtering the results based on the cache, based on an access type, and the type is either like file system accessor or in-memory cache, which is authoritative. You'll see that in a little bit, which is the next slide. So these are, hold on just a second. So this is a bunch of results that you would otherwise get, right? Like this is a mess. Like how do you learn anything from this, right? That's a lot. And so that's why you would usually use a tool like benchstat, which is able to put all these things in context for you, right? It comes with deviation for you, so you can able to see what the deviation is, like in operations, right? It tells you like what's the difference between the columns in here, so that's pretty useful, right? You can see that you're getting some good performance in seconds per operation, and yeah. And maybe here you can actually also see like what the usual output of the benchmark consists of, right? So like the benchmark usually like runs all kinds of parameters, like we said, like record stored is this number, and then it also like it runs bunch of things, right? We've got a concurrency multiplier here. The last number is the number of CPUs that we are running tests with. So, all right. This is, what happened here? I know. So, all right, yeah. This is all that we did. If you would like to have a look at it, some of the things, like this is the design, this is where I was implementing the cache, this is where I was benchmarking it with all the results. That is the end of my presentation.